Welcome back, my math friends. We're going to continue our unit on rational expressions, and we're going to get into the craziest thing of them all, adding and subtracting. And we have completed already simplifying rational expressions. We talked about domain restrictions for rational functions, and we started operating on rational expressions with multiplication. Remember when I talked about multiplication, I said we're going to start with multiplication because it's the easiest of the operations. Although addition is a simple concept, doing it, not so simple. So let's start talking about addition because we've already dove into multiplication. Let's dive into what is addition, and we're going to set up all of these examples. There's going to be a lot of examples for operating on rational expressions because there's just so much that we have to do, and it just gets real funky. So we will go ahead and get started with what is addition, shall we? Okay, let's do that. Then we'll be able to tackle in all of this stuff. So we get into the concept of addition. Now, what in fact is addition? And I've said it before, it is a very, very simple concept. Addition is simply gathering together. Okay, so we're just going to gather stuff together, and that is addition. And gathering together only works if you're dealing with the same unit of measure. Okay, so you can gather cows and dollars and chickens and chickens, but what you can't do is gather apples and frogs. We would just have a certain number of apples and a certain number of frogs. So addition is basically gathering together, but it only works if you're dealing with the same unit of measure. So here's an example. When we're talking about rational numbers, if you have something that looks like this, it would be read as A over B plus C over B. Okay, and we talk about units of measure. Now, what I would say, how I would read this, is that our unit of measure is over B's. Those are our unit of measure. So we're dealing with over B's. That's the unit. Okay, so we have A over B's and C over B's. What that will give us is a certain number of over B's. Okay, so how would we figure that out? Well, A over B plus C over B is A plus C over B's. That's how many over B's there are. So when we're dealing with rational numbers, I consider the denominator a unit of measure, and that just helps with conversions and operating. So if the units can be converted to the same, then you can add them. Okay, so here's an example. If we had A over B plus C over D, as you can tell, we're not dealing in the same unit of measure. All right, so we have over B's and over D's, totally not the same. So the question then becomes, can we convert these units to a same unit? Can we convert these units into something that would be the same? And the answer, of course, if you remember anything about common denominators, is yes, they can be converted. So this is where common denominators come in. All right, so when we look at common denominators, it would be perfect. You can tell that the common denominator of between over B's and over D's is BD. Because if I had multiplied this denominator by D and multiplied this denominator by B, I would have the same unit of measure. So how then could we convert? So we would have our original rational number, and we would want the denominators to be the same, so we'd have to multiply that first denominator by a D. Now, if we multiply a denominator by D, we also have to multiply a numerator by D, so that we're multiplying by the same amount over the same amount. And it's the same thing with C over D. If we're going to convert this unit of measure into a common unit of measure, which would be B over D or BD, we have to multiply it by B. And if we have to multiply the denominator by B, we multiply the numerator by B. Now, why do we have to multiply both the numerator and the denominator? Because of the note. Remember, multiplying something by 1 doesn't change its value. So we can't up and change the value of this number, and we can't up and change the value of this number. And so if we multiply this number by a clever 1, it would keep the value the same. And if we multiply this number by a 1, it would keep the value the same. So we have to think it through. Right now we can convert these into the same unit of measure. So this is what we're looking at, right? If I multiply the numerator and denominator of the first number by d, I'd have AD over BD. If I multiply the second number by b, I want to keep things alphabetical. I should have thought about that here. But in the denominator, notice that they are the same denominator. D times b is b times d. So notice that now that we have converted, right? Notice we have converted our denominators, finding that least common denominator, or that common denominator. We now see that we have the same denominator, the same unit of measure. Now we're dealing with over BDs, right? So we have this many over BDs plus this many over BDs. We now have the same unit of measure. So we would have AD plus BC over BDs, and that would be the same thing as that's it. That'd be the same thing as what we originally started with. So in wrapping up, if you remember the original example, right, our over B's and our over D's, we have to convert that into a same denominator. Okay, so I'm gonna pause here with the crazy stuff because things are about to get nuttier than that. But I'll pause here, and that will be enough to get us going, at least on the first couple of examples. Okay, so as you can see, I'm beginning with elementary level fraction operating. So in our problem 1a, we have a basic operation. We have 5 over 3's plus 5. Now what is this? This is 5 ones. We have to remember that. This is 5 ones. So we have 5 over 3's plus 5 ones. And so we remember that 5 ones also looks like 5 over 1's. Now we cannot add these. They are not the same unit of measure. We can only gather together if we're dealing with the same unit of measure. So we have over 3's and over 1's. That can't work. Can we convert things? Yes, in fact, we can. We can convert our over 1's into over 3's. How can we convert 1's into 3's? Simply by multiplying by a clever 1. If I multiply 1 by something to get 3, that something would have to be 3. And if I multiply the denominator by 3, I have to multiply the numerator by 3. So what I'm actually looking at is 5 over 3's plus 15 over 3's. And if I have 15 over 3's and 5 over 3's, I'm dealing with the same unit of measure. I can then operate on that. So I'd have 5 plus 15 in the numerator, and of course my over 3's is my unit of measure in the denominator. And that would give us, well, 5 plus 15 is 20, 20 over 3's. Ta-da. Okay? So I have to be able to work with the same unit of measure. And that, of course, is very similar to B. Okay, so I have 5 over 3's minus 5, or 5 over 3's minus 5 ones. Okay, so I'm dealing with the unit of measure of ones for the 5. So I have over 3's and ones. And the conversion is going to be the same. To change this into a same unit of measure, I'd multiply by 3. So I'd multiply the top by 3 as well, thus multiplying this entire number by a giant 1, not changing the value. It's still worth 5. Okay, I'm not changing the value of it. I'm just making it look different so I can operate with it. So I'd have 5 over 3's minus 15 over 3's. And again, I have not changed the value of 5. It's still 15 over 3. The value is still the same. And then I can finally operate it with the same unit of measure. Now 5 minus 15, of course, is negative 10. So if I were to add those two expressions, I would have 20 over 3. If I were to subtract those two expressions, I would have negative 10 over 3. And that is how denominator conversions have worked the entire time. But we're going to get a little bit crazy. Okay, so we're going to get crazy with that second example. So now if we had denominators that looked a little bit different. So in this example for 2a, my unit of measure, my denominators are 11z squared. So I'm dealing with over 11z squareds. And as you can see in these two numbers, the units of measure are the same. Okay? And if the units of measure are the same, I can feel free to operate on that. the unit of measure will remain the same, just like it always has. 5 cows plus 2 cows is 7 cows. It doesn't change the fact I'm working with cows. The only thing I need to deal with is adding the numerators, 9 plus x. Now I can't do anything with 9 plus x. 9 plus x is 9 plus x. That's what it is. I could call it x plus 9, but that's not going to change the fact that I can't do anything with this. That is as simple as I can make it. There is no simpler way of expressing that value. Okay, so if I'm dealing with the same unit of measure, no matter what that unit of measure looks like, I can then operate with it for addition. Now, very similarly with the second example for B, we get some crazy things start to happen. We'll see here what's going to happen in a second. All right, so now we have our unit of measure to be x plus 4. That's our unit of measure. So we have over x plus 4s minus over x plus 4s. The unit of measure, or the denominator, is the same, so I can feel free to operate with it as long as it's addition or subtraction. So it's going to remain x plus 4 as my denominator, or my unit of measure over x plus 4s. Now we have to just simply operate the numerator, x squared minus 16. So we have x squared minus 16. Now you may think, can we do anything with x squared minus 16? And you might intuitively think, no, we can't, because we can't combine them. They're not like terms. But then we have to remember simplification. We best recognize what's going on. You have to recognize stuff from the previous units. Remember, x squared minus 16, that is a difference of squares. So you have to recognize what's going on. Now, if you recognize a difference of squares, remember how we factor a difference of squares. Difference of squares factor into conjugates. A plus b, a minus b. So we have to remember that difference of squares factor into our conjugates. So if we're looking at a difference of squares, what is the thing to the second power that gives us x squared? Of course, it is x. What is the thing that gives us 16 when it's to the second power? That, of course, is 4. So we have x minus 4 times x plus 4 because we recognize and we remember. All right, so we have this now as our expression, again, from the previous unit. So if what I just did was confusing, by the way, this is a good time to stop what you're doing. Go back to the video on simplifying rational expressions and make sure you're familiar with all of those examples and what happened. Because remember, we factor first and then we look to cancel. All right, so we have to remember simplification. How did that work? Factor first and then look to cancel. And that's what we're going to do here. We recognize our difference of squares. We're going to factor that difference of squares, and we're going to cancel x plus 4 over x plus 4. So in this crazy setup for b, that whole thing works out to be simply x minus 4. Ta-da! So when we operate addition with that, we have to also recall simplifying to see if we can cancel some stuff to make our lives easier. So it's just a neat thing. So how did this whole thing start? Remember, we had the same units of measure. We can operate the units of measure, and then we look to simplify. So that is just a fun example. So let's do another one. Our third example. We're not getting too crazy just yet. Our third example looks like this. And we can see here, well, we're dealing with the same unit of measure in our third example. Okay, so the unit of measure, of course, is over y squared minus 1. If we're dealing with the same unit of measure, we can simply operate it. But we have to be careful with subtraction. So we'll see what's going to happen in a second. So first things first, we're dealing with the same unit of measure. No harm, no foul. We're going to have y squared minus 1. All we have to do is operate the numerators. So we have 3 plus 2y. and then minus this numerator. Haha, here is the trick. Caution! This is a group. Caution. That second numerator is a group. So when we're subtracting that numerator, we have to subtract it as a group. So let's be cautious when we're working with subtraction, okay? Okay. Thank you, Mr. Katz. So if the denominators are the same, we keep it the same unit and just operate the numerators, but we have to be careful with subtraction. We're subtracting the entire numerator. Okay, so we are subtracting the entire numerator. I'll make that note. We are subtracting the entire numerator. Okay, that's going to either cause or alleviate a lot of issues as we move forward. So all we have to do now is simplify our stuff. We can combine our like terms. Okay, so we would have 3 plus 2y minus 3. So our like terms, 2y minus y, that leaves us with 1y. So I'll just call that 1y. And then 3 minus 3 is 0. So the numerator is going to be left as y. Our denominator stays y squared minus 1. So can we factor the denominator? Yes, we can, but there's no need to in this example. And you'll see why later. But I want to caution you here. Again, another note, canceling only works in addition, or only works in multiplication. So cancel only in multiplication. We cannot cancel these two y's. Can't be done. So this is as done as we can make it. All right, so again, if this is confusing, you have to hit pause and go back to the other video on simplifying rational expressions. Yes? Yes. Thank you, Mr. Katz. All right, let's move on. Next example, because hopefully we're having fun in learning. All right, so the next example, we have 4 over x minus 6 over x squared. What is going to happen? What's going to happen? We cannot operate on these two denominators because they're not the same. Okay? Clearly, these two denominators are not the same. And do you remember what we did in that case? Right? Remember what we did if the denominators weren't the same. We had to find a common denominator and make sure that we're multiplying by 1. So you might think, well, what is a common denominator? Can I multiply this denominator by x squared and this denominator by x? Yeah, you can, but there's an easier way. Or you can totally do that. I'm not going to stop anyone from doing that. But if you're seeing there is a common denominator of x squared. See, this denominator already has x squared. You know what this denominator needs to have this denominator? An x. So this denominator needs an x to match. Right? If that denominator had an x, we'd be good to go. So how can I give that denominator another x? Simple. Multiply it. Bloop. If I multiply that denominator by x, I clearly have to multiply the numerator by x. And there's my clever 1. I have not changed the value of that first number. Okay? So that is a neat thing to remember. I haven't changed the value of that number. So now I just simplify this. I'd have 4x over x squared. See, now I have the denominator I need. Minus 6 over x squared. And there it is. My units of measure are now the same. So all I had to do was recognize that this denominator needed another x to have x squared. And I did that, right? So now that I have the same unit of measure, I can operate the numerators. All right, so 4x minus 6. 4x minus 6 in the numerator. Can we cancel these x's? No, because cancellation can only work in multiplication. This is being added, so we can't cancel that x. Can we factor out a 2 for the numerator? Yes, we can, but it's not going to do us any good, so I don't care if you do or don't, because you're not going to cancel that 2 anyway. So we can call it a day. So that's 4a, right? And that's how we would do that example. And I think I'll do 4b, and then we'll call it a video, because this is going to get a little bit crazier. So now, for example 4b, we have this expression, 3a over 2x to the 5th y squared. And then we have plus 5 over 6x squared y to the 3rd. Okay, now we got to start thinking. Now, what would be a common denominator for these two? Right? So we got a number and a whole bunch of x's and y's. What's going on? So clearly, 2 and 6. What's common between 2 and 6, of course, is 6. 6 is common. So what does this denominator need? This denominator needs a 3. If we multiplied this by 3, we'd be good to go. Both of these denominators have x's, right? This denominator has 5 of them. This denominator has 2 of them. So this denominator needs some x's, right? So this denominator needs 3 more x's. So remember before, this denominator needed a 3, right? So we need a 3. This denominator needs x to the 3rd power. Now what about the y's? This denominator has 2 y's. This denominator has 3 y's. If this denominator had another y, we'd be all set. So we have to think through that. So not only does this denominator need a 3, it needs a 3y. This denominator only needs 3 more x's, so x cubed. And if those denominators had all that stuff, we'd be set to go with the same unit of measure. Okay, the same denominator. So we have to recognize that. That's challenging. How do you get better at it? Practice. Do your homework. Okay, so make sure you are practicing those assignments that I continue to supply for you. So make sure that you are practicing if this is confusing. So we're recognizing that this denominator is a 3y and this denominator is x cubed. So what can we do? Let's multiply by that. Right? So we can multiply this denominator by 3y, and then that means we multiply the numerator by 3y. A clever one. We need to multiply this denominator by x to the 3rd power, so we need to multiply the numerator by x to the 3rd power, and there's our clever one. We have not changed the value of those numbers. Okay, so this is a little bit tricky, right? So now we convert our expressions. In the numerator, we have 9 times ay, or 9a. And then we have 2 times 3, of course, is 6. X to the 5th power stays x to the 5th power. Y squared times y. Y squared times y is, of course, y to the 3rd power. And then we're going to add that to 5 times x to the 3rd power, or 5x cubed, if I knew how to write a 3, over 6 stays 6. X squared times x to the 3rd power is x to the 5th power. And then our y cubed. Now, la, ti, da, look at the magic we have just created. The same unit of measure. We've created the common denominator. As crazy as that looked, we totally did that. So we can operate in the same unit of measure. We can now operate in 6x to the 5th, y to the 3rd. And then all we have to do is operate our numerators. We get 9ay, a plus 5x to the 3rd power. And it can't be factored. There's not a like term. This is as done can be. And so we have simplified that expression. And I think at this point, I'm going to pause and end this video because we're going to have a much more difficult time with polynomials. So I'll get into that in the next video. We're going to call it a day here. Hopefully you learned something. And remember, please, please, please practice. You have to practice this if you're going to get better at it because you start recognizing things a lot easier. All right, take care. I'm outie.